hello everybody, and welcome to your big lesson here in kinematics. We're going to talk about the big three kinematic equations today. So my name is Mr. G, and let's get right to it. So first thing I'm going to bring up is this idea that we have an equation for velocity already, but the problem with it is we've defined it as the change in distance over change in time, but really what that's going to do is that's going to give us the average velocity over that distance. It's not going to give us any instantaneous velocity at a given time. So really, for accelerated motion, it's not going to do us much good. What will do us some good, though, is we can now find average velocity with a different manner by using this equation right here, which is really just the final velocity plus the initial velocity divided by 2. It sure sounds like you're taking the average of two values, and in this case, you actually are. So it's pretty neat that physics allows us to simply take two physical quantities and average them out like that. So in order to solve these problems with uniform acceleration, we need to use what we call the big three kinematics equations. So let's get right to it. With every one of these equations, I want every single one of you to start getting into the habit of listing these particular physical quantities. The first one is the final velocity. You're going to see this as a regular v or a vf, but you should always list if we have it or not. If we don't have it, put a question mark. Second one, initial velocity. That O underneath is not an O at all. It's called a naught. So V naught or anything naught means initial state of whatever quantity that is. A is, of course, our acceleration. D is our displacement or distance. Remember, they sometimes coincide. And T is our time. With every single question, you should always list these 5 quantities, whether we have them or not, and that's going to help you decide which of these big three to use. Now, you'll notice that our velocities, acceleration, and distance, those are all vector quantities. Remember when we talked about this idea of signs on values mean direction in physics? Well, that's going to be the case here. So you are going to need to self-impose what way is positive and what way is negative. Now, again, we've brought up the idea that right is positive, left is negative, up is positive, down is negative. But really, you can go any way you want so long as you're consistent. So as long as you're consistent, you shouldn't have a sign problem at all. Let's get to the first big three equation, and that one's going to be one that we've already derived before, and this is the idea that the final velocity is equal to the initial velocity plus acceleration times time. And a question that we would see where this equation would be relevant is right here. A squad car traveling at 7 meters per second east speeds up to 22 meters per second east in 1.7 seconds. What is its acceleration? So as I said, let's always write down what we know. So our initial velocity is 7 meters per second. Our final velocity is 22 meters per second. Do we have a distance? No. Do we have an acceleration? No. Do we have a time? Yes, we do. It's 1.7 seconds. Now you have to ask yourself, do we need distance to find acceleration? And in this case, no, we don't, because we have our velocities and our time. We can use VF equals VI plus AT, and we're going to solve for acceleration. So like I said, and I'm going to sound redundant when I say this, solve for the variable first, then plug in the values. So we're solving for A. So I'm going to skip some steps here. I'm going to subtract initial velocity from both sides and then divide by time so that I get acceleration is equal to VF minus VI over T. For those of you in my class, if you go from that initial equation to this equation and you don't show any steps, be careful, because some of you are going to mess up on the signs, so I would suggest showing those steps. But I have enough degrees to say I can just skip along. So we have this here. What do we do now? Let's plug in the values. Our final velocity is 22, our initial velocity is 7, and our time is 1.7 seconds. Notice all those are in SI units, so we're good to go. That means we get a final solution of 8.8 meters per second squared. Is that our final solution? No. Why? Because acceleration is a vector, which means we need a direction. Well, if we're starting east and we speed up traveling east, that means acceleration has to be in the direction of motion, which means this acceleration too is in the east. So that's your final answer. For those of you that are wondering what I look for when we're dealing with writing syntax, here it is. You've got your table on the left, you've got your equation on the right, and you solve, and you notice all the equal signs are stacked up and you got a big box around your final solution because you are proud of it. So sometimes the work gets a little messier. Heck, even I do that. But try to be as neat as you can so that lowly physics teachers like me will be able to follow. All right, let's get to the second of the big three equations. And in that case, we're going to deal with an equation that's going to help us find distance. Distance is equal to VIT plus 1/2 AT squared. Now, for those of you that have been through Pre-Calculus 11 far enough, you know that this is a quadratic equation. That's nice. Think back to our graphing of distance versus time of a accelerated object. It was a curve. Well, guess what? It was a quadratic. How about that? So, let's take a look at a question like this. A sprinter starts from rest and accelerates uniformly. He travels 100 meters south in 9.69 seconds. What was his acceleration? So, some key features here. We're starting from rest. The acceleration is uniform. That's good. That means it's going to be constant, which means it's going to be a horizontal line, which is all we know how to deal with. He travels 100 meters to the south in a time of 9.69 seconds. What is his acceleration? Let's figure it out. Initial velocity is 0. Why? It's at rest. Our final velocity is equal to, we have no clue. Our distance is equal to 100 meters. Our acceleration is equal to, we still don't know. And our time is equal to 9.69 seconds. So we're looking here for acceleration. So we see we have D, we have VI, and we have T. D, VI, T, A, T. We're looking for A. Life is good. Let's use this equation. D equals, I'll say V naught T this time, plus 1/2 AT squared. Now, something really nice happens, which is going to make the algebra of this much simpler. If our initial velocity is 0, initial velocity 0 times whatever is going to equal 0. So it cancels out, giving us a much easier equation of just 1/2 AT squared. That will happen more often than not, but realize that sometimes our initial velocity will not be 0. In this case now we're solving for A. Again, I'm going to say I get to skip a couple steps, and A is equal to 2D divided by T squared. If anybody has a problem with that step, please ask me, because I'd be happy to explain. So we have the equation. It's solved for all the variables. Now let's go ahead and plug them in. So we have 2 times our distance of 100 meters. And we're dividing by our time, which is 9.69 seconds squared. Again, everything is in SI units, which is super important. That means that we're going to get an answer in meters per second squared. And when we do so, we should end up with 2.13 meters per second squared. Again, acceleration is a vector, so we need a direction. Well, he traveled 100 meters south, which means we accelerated from rest to some speed going south. That means it was also pointing south. We sped up to the south, therefore our acceleration's in the south. Okay? Wicked. So our third and final equation looks a little something like this. We're going to say that VF squared is equal to VI squared plus 2AD. So notice in this case we don't have a time, we just have distance, acceleration, and velocities. This is going to be a different type of equation. It should give you a hint when you have a question that doesn't have a time in it that you probably will use this one. Let's take a look at an example. A banana boat accelerates uniformly from 15 kilometers per hour west at 2 meters per second squared west. How far has it traveled when it reaches 30 kilometers per hour? So, first thing, let's always list what we have. Our V initial is equal to 15 kilometers per hour. Our V final is equal to 30 kilometers per hour. Do we know the acceleration? Sure we do. It's 2 meters per second squared. Do we know the distance? No. Do we know the time? No. Do we need the time in order to find the distance? Absolutely not. We have an equation that does it for us. But we do have a serious problem, don't we? Our velocities are in non-SI units, so we have to convert them. Now, 2 ways to do it. You could brute force it, or you could use that nice little 3.6 trick. I'm going to say I'm feeling a little lazy. Let's just divide by 3.6. If you don't know where that comes from, don't use it. Otherwise, people go, what are you doing? If we convert these, we end up with 4.17 meters per second and 8.33 meters per second. Perfect. Now all the values are in SI units. Let's solve this bad boy. Vf squared is equal to Vi squared plus 2AD. We need to solve this equation for D. I'm going to skip some steps and tell you that D is equal to Vf squared minus Vi squared over 2A. If you don't know where that came from, talk to me because it's simple algebra. Now that we're here, let's plug in our values. We have 8.33 squared subtract 4.17 squared divided by 2 times 2. And you should end up with an answer of 13 meters. Now notice, there is no direction in this case. Why is that? Because we're just talking about distance, right? Now, we can assume that the distance was in its direction of motion, but again, we're not asking for displacement in this case. This is asking how far has it traveled. It's the quantity between 2 points. That's just distance. That's a scalar quantity. We got through some of those examples. Here's some now where we're not going to tell you what kind of equations you have to play with, and you just have to figure out which equations you want to use yourself. Again, I would suggest listing out the variables before you solve it. I'm going to give you some help right now. The rocket truck is traveling at 16 meters per second when it passed by a plane. It immediately hits the jets and accelerates to 14 meters per second squared for 3.25 seconds. And the question is, what final velocity does it reach? So let's find out. Do we know the final velocity? No. Do we know the initial velocity? Yes. It's 16 meters per second. Do we know the acceleration? You bet. It was 14 meters per second squared. Do we know the distance? No. Do we know the time? It's 3.25 seconds. So we need VF. We have VI. We have A. We have T. Whoo, that sure sounds like VF equals VI plus AT to me. In this case, we don't even have to do any algebra. All the variables are in the right places, so let's just plug and chug. We have 16 plus 14 times 3.25, which equals 61.5 meters per second as your solution. Now, you'll notice that there's no direct statement of which way it's going. It is a vector. So what do we say about this direction? Well, in this case, we're just saying that positive is equal to the direction of motion. Now, it depends on who's grading your stuff. For me, I need this stated because I want to make sure that when you get a solution and it is a positive value, that you understood that that meant that that velocity is in the initial direction of motion. Why? Because you're going to get cases where there's accelerations going against motion, and you're going to have to make sure that's clear. So it's a silly little thing, but it's really important, so make sure you say it. So for second A, also known as B, how far does it travel in this time? So now we're looking for the distance. Well, remember, I said if you're looking for distance, there's really two equations. You're going to either have VF squared equals VI squared plus 2AD, or distance equals VIT plus 1/2 AT squared. In general, I say use the equation that's simpler. In my mind, this equation is simpler. So VF squared equals VI squared plus 2AD. We're going to solve for D. D equals VF squared minus VI squared over 2A. Let's plug in those values. We've got 61.5 squared minus 16 squared divided by 2 times 14, and that's going to give you a final value of about 126 meters. Again, we don't need to establish a direction. Why? Because distance is in fact a scalar. Displacement is the vector. Okay, so little tricky, but notice how listing that table at the beginning really helps you along the way. Let's deal with another one. An arrow strikes a can at 32 meters per second and exits at 31 meters per second. If the arrow is 42 centimeters long, find its acceleration as it pierced the can. Ignore the width of the can. So that's super nice. The question writer saying, don't worry about the width of the can, because when you have to deal with that, well, then there's some acceleration that happens through the can, and then actually through the empty part of the can, and the other part of the can, blah, blah, blah. It's a much more intricate question when you have to deal with that. So, yay, thank you very much. Let's write out what we know. We know that our initial velocity is 32 meters per second. We know that our final velocity is 31 meters per second. Do we know what our acceleration is? Nope. Do we know what our distance is? Yep, it's 0.42 meters. And do we know what our time is? No, we don't. So, we have distance, we have VF, we have VI, we need A. Again, that sounds like VF squared equals VI squared plus 2AD. We have to solve for A. I'm going to skip some steps, and A is equal to VF squared minus VI squared divided by 2D. Plug in our values. Our VF is equal to 31 squared minus VI, which is equal to 32 squared, divided by 2 times our distance, which is 0.42 meters. Now notice I glossed over the idea. It was 42 centimeters. Look what I put it in. That's pretty important. Because we're going to end up with an answer in SI units. It's going to be negative 75 meters per second squared. What does this negative mean? Well, that means that it's opposing motion. So that means it is directly opposing motion. So it is really important that you understand that. All right. One more time and then I'll set you free. A BMW and an F1 car both cross the finish line traveling at 200 kilometers an hour. It's pretty slow. The BMW comes to a stop in 4.05 seconds and the F1 in 2.12 seconds. How much further did the BMW travel while stopping than the F1 car? So, I hope by reading this you go, it sounds like a two-parter to me. Absolutely. Because now we need to find quantities for both cars. Let's write what we know. Do we know final velocity? You bet we do. It's nothing. We want to come to a stop. Do we know initial velocity? Yep, it's 200 kilometers per hour. And for those of you that are paying attention, we need to convert that into SI units, so that's equal to 55.6 meters per second. Do we know the time? Yeah, they're given for both cars. So that's cool. That's going to be useful. Do we know the distance traveled? Well, no, we don't. And do we know the acceleration to do so? Also, no, we don't. So, is there any way to get distance only knowing time and the two velocities? Let's think back to our big three equations, and that's a big fat no. So, let's figure out what we need to get there. Well, when we find distance, I love using VF squared equals VI squared plus 2AD, where I will solve that. D is equal to VF squared minus VI squared over 2A. Okay, so I have VF, I have VI, but I don't have A, so we have to find the acceleration. Can we find the acceleration with the information we have? You bet we can. We have VF, we have VI, we have T, so now we're going to use VF is equal to VI plus AT. Solving for A is equal to VF minus VI over T. Cool. So this is step 1 here. This is step 2 over there. So let's deal with it. We'll go BMW. The acceleration is equal to, well, VF is 0 minus 55.6 divided by, how long did it take to stop? 4.05 seconds to give us an acceleration of negative 13.7 meters per second squared. Now, why is it negative? Because we had a negative on top, we have a positive number on the bottom. Isn't that nice? The negative shows that it's directly opposing motion, which came out of the equation alone. As long as we're consistent with our signs, all the signs of everything should work out for you. So the acceleration was supposed to be negative, and it is. What about the F1 car? Well, it's the same equation, 0 minus 55.6, except it slowed down in 2.12 seconds to give us a total acceleration of negative 26.2 meters per second squared. So this is where you have to stop and think for a second. Should the acceleration of the F1 car be faster than the acceleration of the BMW car? Absolutely. It was going just as fast and it slowed down in less time, which means the deceleration should be faster. So there we go. Good, accelerations are nice. Now what do we do with it? Now we need to find how long it took them to stop. Or not how long, but how far they stopped in. So we go back to BMW. Now we're in phase 2. Distance equals VF squared, which is 0, subtract VI squared, which is 55.6 squared, and we're going to divide that by 2 times negative 13.7. Uh-oh, are we going to end up with the distance being negative? No, because we have a negative there, we have a negative there. They're going to cancel to give us a total distance of 112.8 meters. What about the F1? Sorry for the messiness. We're getting crammed up here. Distance is equal to 0 minus 55.6 squared divided by 2 times the acceleration, negative 26.2. And we're going to end up with a distance here of 59 meters. So we have our distances that it took to stop. The question is, how much farther did the BMW travel while stopping in the F1 car? So we can say the BMW traveled, here it is, 112.8 minus 59, which equals 53.8 meters more. And just like that, my friends, you are done. So it looks tricky because you got a lot of steps, but again, we broke it down using our initial table. We said we needed the acceleration in order to find the distance, so we went that route. Now, could you use the other equation out of the big three? Sure you could, right? There's an acceleration there, there's a distance there. Either way you went, you had to find the acceleration first. So after you find the acceleration, whichever one you use to find distance is up to you.